Hello, in this video we will study continuous functions. The concept of continuity is an extremely powerful and important notion in real analysis with huge applications. All of the most useful elementary functions in real analysis like polynomials, trigonometry, exponential, log functions are everywhere continuous on their domain. So given a set of real numbers a, and let f be a function between a and r, and let c be an element in the domain of f, we say that f is continuous at c if for any epsilon which is positive there exists a delta which is positive, which also often depends on epsilon and c, such that if x is in a and if the distance between x and c is less than delta, then the distance between f of x and f of c will be less than epsilon. Let f be a function between a and r. We say, and suppose that c is a cluster point. Suppose that c is a cluster point of a. Then f is continuous at c if and only if all three of the following holds true. First, f is defined at c. In other words, c is in the domain of f. B, the limit of f of x when x is approaching c is equal to some real number L. And thirdly, L must be equal to f of c. So in the case where c is a cluster point, the concept of f is continuous at c is equivalent to all three of these statements. Next, the sequential criteria for continuity. First, if a function is not continuous at c, we say that f is discontinuous at c. And the discontinuity criteria is stated as follows. Criterion: let a be a subset of the reals, and let f be a function between a and the reals. Next, let c be an element of a. We say that f is discontinuous at c if and only if there exists a sequence, say xn, such that the limits of xn as n is approaching infinity is equal to c, but the limits of the image of the sequence xn, which is f of xn, as n is approaching infinity is not equal to f of c. So in other words, the sequence f of xn is not convergent to f of c. As an illustration, here is a good example. Let f be given as follows. It's 1 if x is non-negative and -1 otherwise. So its graph is looking like this. Now let xn be the sequence given by -1 power n over n. Then clearly you will agree that the limit of -1 power n over n as n is approaching infinity is 0. So this sequence is going to 0. Now note that the limit of f of x to k as k is approaching infinity is the limit of f of 1 over 2k as k is approaching infinity, and since 1 over 2k is positive, then this will be the limit of 1 as k is approaching infinity, which is 1. Okay, all right, now the limit of f of x to k plus 1 as k is approaching infinity is the limit of f of -1 over 2k plus 1 when k is approaching infinity. And because this is always negative, the input is always negative, then the output is -1. So that will converge, this subsequence will converge to -1. So we have found, so there exists two subsequences of f of xn converging to two distinct limits. Thus, the sequence f of xn is not convergent, is divergent, which clearly means that it does not converge to f of 0. So we have now found a sequence xn which converges to 0, but its image does not converge to f of 0. So thus f is discontinuous at 0. Let A be a subset of the reals, and let f be a function between a and r. Next, let x be a subset of a. We say that f is continuous on x if f is continuous at every point little x and big X. So for example, if we let f be the map between R and R such that f of x is equal to x cubed, then so first we note that since f is a polynomial, the domain of f is R, right? And also, so for any C in R, from what we've seen in our previous section, the limits of x cubed as x is approaching c is precisely c cubed, which is f of c. Right, so thus f is continuous at every point in R, and we conclude that f is continuous on R. So let rho be a function between R take away 0 and R such that rho of x is equal to 1 over x squared. And let's so given C, which is in R, C is not 0, by the product rule for limits, we know that the limit of x squared when x is approaching c will be c squared. Next, by the quotient rule of limit, we know that the limit of 1 over x squared as x is approaching c will be 1 over c squared, which is precisely rho of c. Right, so thus rho is continuous at every point c in R take away 0, and we say that rho is continuous at on R take away 0. Now I would like to make a short remark here. So note that rho is not continuous at 0 because 0 is not in the domain of rho. Another example, let f be a map between R and R such that f of x is equal to 1 over x squared if x is not 0, otherwise f of x is 0. Alright, now I would like to show that the limit of f of x when x is approaching 0 is not equal to f of 0, which is 0. So to this end, we want to show, I would like to show the following. I would like to show that there exists some epsilon which is positive, such that for all delta which are positive, there exists x in the domain of there exists actually x non-zero, such that if the distance between x and 0 is less than delta, such that this holds, and somehow the distance between 1 over x squared and f of 0, which is 0, is greater or equal to 1, to epsilon here. Okay, so I will let epsilon be equal to 1 to make this happen, and I'll pick any delta which is positive, and I'll claim that there exists x which is non-zero, such that the distance between x and 0 is less than delta, and somehow the distance between 1 over x squared and 0, which is 1 over x squared, will be greater than 1. And to make this happen, it is enough to pick x, non-zero x, such that x is less or equal to 1, and also less or equal to, absolute value of x is less or equal to 1, and also less or equal to delta, right? Because as long as the absolute value of x is less or equal to 1, then we'll get that the absolute value of x squared will be less or equal to 1, which is equivalent to the fact that 1 over x squared is greater or equal to 1. Okay. All right, so no matter how how small delta is, if I pick x inside an open set, I'll pick x inside an open set around 0, such that the distance between x and 0 is less than 1, then automatically I'll get that the distance between 1 over x squared and 0 is greater than 1, which then violates the fact that the limit of f of x when x is approaching 0 is equal to f of 0. So we can then claim that f is discontinuous at 0. Alright, so let's consider another example. Let f be a map between R and R such that f of x is equal to x sine of 1 over x if x is not 0, and 0 if x is equal to 0. Alright, now note that for any non-zero x, the absolute value of x times sine of 1 over x is it's this product, and clearly notice that this was always less or equal to 1, so this will be less or equal to the absolute value of x times 1, which is the absolute value of x. So thus for any x which is not 0, we know that 0 is less or equal to x times sine of 1 over x, which is less or equal to the absolute value of x. Therefore, the limits of 0 as x is approaching 0 is going to be less or equal to the limit of x sine of 1 over x as x is approaching 0, which is less or equal to the limit of the absolute value of x as x is approaching 0. So and notice that this will go to 0, right, and then this will go to 0, and by the squeeze theorem, we get that the limits of the absolute value of x sine of 1 over x when x is approaching 0 is 0. Alright, now let's epsilon be some positive number. So let's epsilon be positive number. Then there exists delta, which is positive, clearly usually depending on epsilon, such that if this condition holds, then the distance between, then we can prove that the absolute value of x sine of 1 over x, this thing here, right, the distance between this can be made less than epsilon. So in other words, so if we so there exists, in other words there is a delta which is positive. I will I'd like to reformulate this a little bit. So let delta be as described. Now assume that this condition holds, then is precisely the same thing as what we've written earlier. Which is less than epsilon. Therefore, the limit of x sine of 1 over x as x is approaching 0 is 0, and we conclude that the given function is continuous at 0, since 0 is equal to f of 0. Let f be a function between a and the reals such that f of x is equal to 1 if x is a rational number, and 0 if x is not a rational number. Now let q be some rational number by the density. So next, let's xn be a sequence of irrational numbers such that the limit of xn as n is approaching infinity is equal to q. And I like to comment here that this can be achieved as a corollary of the density of the rationals. Right? We can find a sequence of irrational numbers which is convergent to q. Then for any natural number n, it is clear that f of xn must be 0, since xn is not a rational number. Okay, by using our definition of f. So the limit of f of xn as n is approaching infinity is the limit of the constant sequence 0 as n is approaching infinity, and that will be 0, which is not f of q, since q is a rational number, which is 1. Okay, all right, so that means that this function is not continuous at the rationals. Now let's play the same game on the other way around. Let's suppose that s is an irrational number. Now I will let yn be a sequence of rational numbers such that the limits of yn as n is approaching infinity is equal to s, and this can be achieved by the density theorem. So we can use the density of the rationals, or the denseness of the rationals here. Okay, all right, so then for any natural number n, we have that f of yn is equal to 1, and clearly this means that the limit of f of yn as n is approaching infinity will be equal to 1 right? Because f of y, this is a constant sequence, which is not equal to f of s, which is 0, because here s is not a rational number, right? So f is not continuous at the irrationals, and then we conclude that f is discontinuous everywhere. And so this is an example of a function which is discontinuous everywhere. I claim that the absolute value function is continuous everywhere. It's continuous on R. So to this end, let f be a function mapping R into R such that f of x is equal to the absolute value of x. Then I would like to prove that f is continuous on R. So to this end, it's enough to prove that f is continuous on at every real number a. So let a be some real number, and fix some epsilon which is positive. Next, let delta be some positive number. I will select my delta to be precisely equal to epsilon, and we'll see in a minute why. Now assume that the distance between x and a is less than delta. Then f of x minus f of a, the distance between f of x and f of a will be the distance between the absolute value of x minus the absolute value of a. And by a corollary of the triangular inequality, this thing here is less equal to x minus a. By a corollary of the triangle inequality, and this will be less than delta, which we set to be equal to epsilon. Now you see why we let delta be equal to epsilon, because we would like to make the distance between f of x and f of a less than epsilon. Therefore, we conclude that the limit of f of x as x is approaching a is equal to f of a, and f is continuous at a. Thus, f is continuous on R. Next, I will prove the following. There exists a function f which is mapping the reals into the reals such that f is discontinuous everywhere, but somehow f times f, which I will denote f squared, is continuous everywhere. So this example goes as follows. I will let f of x, so for the proof, let f of x be the function which is 1 if x is a rational number, and -1 if x is an irrational number. Now let's let q be some rational number, and let xn be a sequence of irrationals converging to q. Then you can see that the limit of f of xn as n is approaching infinity will be the limit, because every xn is irrational, so this will be the limit of -1 as n is approaching infinity, which is -1, which is not equal to f of q, which happens to be 1, because q is a rational number. And similarly, if we let s be some irrational numbers, let yn be a sequence of rational numbers such that the limit of yn as n is approaching infinity is equal to s. Next, the limit of f of yn as n is approaching infinity, so every yn is a rational number, so this will go to 1, and clearly 1 is not equal to f of s, which is -1. So therefore this function f is nowhere continuous. Now let x be some rational number, then f of x times f of x will be, right, that's f of x square, and that's 1 square, right, which is 1. And if we let x be some irrational numbers, then f of x times f of x is -1 square, and that's still 1. So for any real number x, f of x square is the constant function 1, the constant function. Thus, the square of f is continuous on all real numbers. Right, so that's a nice example of a function which is nowhere continuous, somehow its square is continuous everywhere. Now let h be a function between 0 to infinity and r. So it's mapping the set of all positive numbers into the reals such that h of x is 0 if x is greater than 0 and x is not irrational, and 1 over n if x is greater than 0 and x is a rational number such that x is equal to m over n, is in its reduced form. So that means that m and n have no common factors. Okay, now let a be some positive number which is also rationals. Next, I will let xn be a sequence of irrational numbers such that the limits of xn as n is approaching infinity is equal to a. So we pick a sequence of irrational numbers convergent to some rational number a. Then for any natural number n, we notice that by definition h of xn will be 0, right? Thus the limit of h of xn as n is approaching infinity is the limit of the 0 sequence, which is 0. Now, on the other hand, note that the limit of h of xn as n is approaching infinity must not be equal to h of a, because h of a is a strictly positive number, right? Whatever a is, a has to be, we should be able to write a as a rational number of the type s over t, where s and t have no common factors, and h of a by definition will be 1 over t, which must be positive. Okay, so that means that the limit of h of xn cannot be equal to h of a. So we can then say that h is discontinuous at every rational number. All right, now let's look at the irrational numbers. So let's b be some positive numbers such that b is irrationals. Okay, now let's epsilon be some positive number, and by the Archimedean property, there exists some natural number n such that 1 over n is less than epsilon. Okay, now let's suppose that delta is some positive number. Then I claim that the open set b minus delta b plus delta contains at most a finite number of elements of the form m over n, which are rationals, such that somehow little n is less or equal to big N. So indeed, here is the reason why. Notice that if m over n is in the open interval b minus delta and b plus delta, this is equivalent to the fact that the distance between m and n, m over n, and b must be less than delta. And this is essentially, well, here's an easier way of writing it. It means that b minus delta is less than m over n, which is less than b plus delta. And then this means that multiplying everything by n, we get that n times b minus delta is less than m, which is less than b plus delta n. So first of all, n is a natural number, and since big N is a natural number, there are finitely many numbers smaller than n, right? Namely, there's 1, 2, 3, all the way till n minus 1. Okay. On top of that, so we already know that the denominators. So if there are only finitely many denominators which are less or equal to n. On top of that, m must satisfy the following criterion. M must be less or equal to b plus delta times n, right? And so then if little n is greater or equal to big N, then it must be the case that and if m over n is in the set b minus delta b plus delta, then it must be the case that m must be less than b plus delta times n, which will be less or equal to b plus delta times n. So there are also finitely many little m which satisfies this inequality. So the point being here that there are finitely many m and n which are natural numbers such that m is less or equal to b plus delta n, and also little n is less or equal to n. Okay. All right. So the point here is the following. If we so this set here, if I consider this set, the open interval center at b and radius delta, this set will contain finitely many elements of the type m over n, which are rational numbers such that m over n are natural numbers and n is less or equal to big N. So then I can make this. So we'll proceed as follows. Let's okay, I will consider this set here X. Let me redraw my picture here. This is B, and this is B minus delta, and this is B plus delta. And suppose these are all such numbers. So let X be the set of all m over n, which are rational numbers such that m and n are natural numbers, and on top of that n is less or equal to n. Okay, now I will let delta be the minimum of the following: the set of all absolute value of the type b minus little x, such that little x is in the set big X. We already know that x is finite. X is a finite set, and we don't want x to be equal to b. So this thing here will be, let me call, because I already use a delta, let me call this here delta 1. This will be a positive number, and so if we fix such a delta 1, then now assume that x minus b is less than delta 1. Well, if x is a rational number, we already have settled this, and so now if x is an irrational number, then it must be of the type m over n, and by construction little n must be strictly greater than capital N, right? Okay, so then so if we fix x such that, so assume that x is assume that x is a real number. So let me rewrite this. Assume x is some real numbers greater than 0, such that the distance between x and b is less than delta 1. Then h of x minus h of b will be h of x minus 0, which is the absolute value of h of x. And notice that in any case, whatever this number is, it must be less than 1 over n, because if x is an irrational number, it must be 0. If x is a rational number, it has to be of the type m over n, and in this case n must be greater than capital N because of our construction of delta 1, and taking the reciprocal of this, we get 1 over n is less than 1 over big N, which is less than epsilon. All right, so then we have then obtained the following: thus h is continuous at the rational b. So to summarize, what we have done so far is the following: if we let h of x be the function which is 0 if x is positive and x is not a rational number, which is 1 over n if x is positive and somehow x is a rational number, and x is equal to m over n, is in reduced form, then h is discontinuous. H is discontinuous at every rational number but it is continuous at all irrational numbers. Okay, so this is a difficult example. It's the proof is not completely easy to follow, so you may need to rewind the tape, pause, and try to process the information at your own pace.